Hey, this is Mr. Ayton. This is Pre-AP Chemistry, and we are back in a new semester, and we're in a new unit, Unit 9 Gases, for Week 19. So if you've been to Taco Bell recently, these are going to be some more gas problems. Week 19, what are we going to learn? We're going to learn gas laws, all the different gas laws, whether we talk about Boyle's law, Charles' law, Gay-Lussac's law, the combined gas law. We're going to be looking at the properties and particulate models of gases. And last, we're going to look at the ideal gas law. So let's go to our gas laws. The first gas law is Boyle's law. And Boyle's law is dealing with the pressure and volume of a gas, the relationship between pressure and volume. You can see the number of particles of the gas are staying constant. The absolute temperature of the gas is staying constant. And all we're really changing is the pressure and the volume. And it is an inverse relationship, as you can see the graph here. It's an inverse relationship, and the equation is P1V1 equals P2V2. And the volume of a gas is not the individual volume of the particles, but the size of the container it's in. So as you can see, as the volume of the container gets smaller, you can see the pressure goes up because there's less space for the particles to move, and so the particles begin to collide off the sides of the container, and therefore the pressure increases. So as the volume goes down, the pressure goes up, and that is an inverse relationship for Boyle's law. That's our first law. The second law is Charles's law. Charles's law is dealing with volume and absolute temperature. You can see I did not say temperature, I said absolute temperature, which means our temperature needs to be in Kelvin. If you have degrees Celsius, you need to add 273 to it to get to Kelvin, and the equation for that is V1 over T1 equals V2 over T2. The volume over the temperature, as the volume changes, the temperature changes. And this is a proportional relationship, a directly proportional relationship, which means if you double the absolute temperature, if it goes from 100 Kelvin to 200 Kelvin, the volume will double as well. And if you can see, the temperature, as the temperature increases, the kinetic energy of the particles increase. And as the kinetic energy of the particles increase, they begin to move at a faster speed, which, in order to compensate for the change in the pressure, the volume increases. So as the temperature increases, the kinetic energy of the particles increase, the speed of the particles increase, and therefore the volume of the container increases, the volume of the gas. Last is Gay-Lussac's law. Gay-Lussac's law looks a lot like Charles's law, except for this is pressure and temperature. This is when the volume is staying constant and the number of particles is staying constant. And so the equation is P1 over T1 equals P2 over T2. Again, the temperature is absolute temperature, not degrees Celsius, not Fahrenheit, but absolute temperature in Kelvin. And this is a directly proportional relationship as well. And so you can see, as the temperature increases, as we add more kinetic energy, the particles begin to move faster. The particles themselves have more kinetic energy. And as the particles move faster, they have a greater frequency of collisions with the sides of the container, and therefore the pressure increases. So as the temperature increases, if the absolute temperature doubles, the pressure will also double as well. Well, what can we do? We can take all three of these gas laws, whether it's Boyle's law, Charles's law, and Gay-Lussac's law, and combine them into what we call the combined gas law. And as you can see, if the temperature is staying constant, we can eliminate temperature from there, and we have P1V1 equals P2V2. If the pressure is staying constant, we have Charles's law, V1 over T1 equals V2 over T2. If the volume is staying constant, we can eliminate volume, and we have Gay-Lussac's law, P1 over T1 equals P2 over T2. Or we can have more things changing than just one of these things, and we can have a lot of things changing. You can see here in this problem, we have a sample. We have a 2-liter sample, that's our volume, of helium gas at 25 degrees Celsius and 2 atmospheres is heated. So that's my initial. So we have 2 liters, 25 degrees Celsius, and 2 atmospheres. And those are going to be my initial things. And so my P1 is going to be 2.0 atmospheres. My V1 is 2.0 liters. And my T1 is going to be 25 degrees Celsius plus 273, or 298 Kelvin on the bottom. We have to always put it in absolute temperature. And then you can see the temperature is changing to 50 degrees. So the temperature is going from 25 to 50 degrees Celsius. But remember, that's not doubling the temperature. It's only going up by a slight amount. We're going from 298 to 323. And you can see the volume is 3.0 liters here, which means we're looking for the new pressure of the gas here, the new pressure of the gas. So you can do algebra for this. You can cross multiply if you want. I like to do it this way. I like to do my algebra this way is you can see the 3 liters is being multiplied, which means we're going to move 3 liters on the bottom, 3.0 liters. And the 50 and 273 is obviously 323. That's going up top. So 373 degrees Kelvin, okay? And so anything on the bottom, we're multiplying. Anything on the top, we're dividing. And now I can put all of this in my calculator. I'm going to put 373 times 2 times 2 divided by 3 divided by 298. Keep in mind you want to divide by both. And you can see the Kelvin cancels out with our Kelvin. Our liters cancels out with our liters, which means our pressure is left in atmospheres. And we end up getting 1.67 atmospheres. So you can try that in your calculator. And we can use the combined gas law. Again, we can use the combined gas law whether we're doing Boyle's law, like this, whether we're doing Charles's law, which in Charles's law the pressure is staying constant, or last but not least we can do Gay-Lussac's law. Gay-Lussac's law is when the volume is constant, and you can see the combined gas law has all 3 gas laws combined together. Okay, let's take a look at some gas properties. Gas properties is what are each one of these variables of pressure and temperature and volume and moles, what are these all related to when we talk about our gases? And gas pressure is all about the collisions. So gas pressure is all about the collisions of the particles with each other as well as the sides of the container. That's what develops the pressure of a gas, the pressure of a gas. The temperature of the gas is a measurement of the average kinetic energy of the particles. So temperature and average kinetic energy are related, okay? The volume of the gas is not the volume of the individual particles. They're negligible. It's the volume of the container is the volume, okay? So if you're in a room with a bunch of gas, the whole room's volume is the volume of the gases. And the number of moles is obviously the number of particles. It's the number of particles. And so when we talk about pressure, we're going to talk about collisions. Temperature, we're going to talk about average kinetic energy. Volume, we're talking about the volume of the container. And moles, we're talking about the number of particles. Which brings us to what we call the ideal gas law. I hope you can see PV over T is this combined gas law is in this PV equals nRT. We multiplied the temperature on this side, and you can see we have the number of moles, which is N. N is the number of moles, and R is called the universal gas constant. The universal gas constant is 0.08206 liters, atmospheres, moles, and Kelvin. Which, why do we put all these units here? Liters, atmospheres per mole per Kelvin is you want your volume in liters, your pressure in atmospheres, your moles in moles, and your temperature in Kelvin to use the ideal gas law. And this ideal gas law only works for ideal gases, okay? So let's take a look at using this ideal gas law. We have 2 atmospheres, which means we're going to put 2.0 atmospheres. We have our liters, 2.0 liters. And our temperature is 25 degrees Celsius, which is 25 plus 273 is 298 Kelvin. And of course, R is a constant. R is 0.08206, okay? And you can see my pressure was in atmospheres, my volume is in liters, my temperature is in Kelvin, which means we can use the universal gas constant, which means I'm trying to find the number of moles of helium gas. So we're going to take 2 times 2, divide by the universal gas constant, divide by 298. Keep in mind we have to divide by both. And that gives us a number of moles, which is 0.164 moles of helium. Again, We always put our number, our units, and what it's assigned to. 0.164 moles of helium. Which means, what can we do if we know the number of moles? We can take 0.164 moles of helium, and think back to the first semester. We can multiply by the molar mass of helium, which is 4 grams per mole. And if I multiply that by 4, I can know that this is 0.654 grams of helium. So I can know the mass of helium by using PIV-NERT, the ideal gas law. Okay. So what did we go through today? We went through the combined gas law, Boyle's law, Charles's law, Gay-Lussac's law, and we went through PIV-NERT and what all those variables mean in gases. So hope this helps. I'll see you in class, guys. Catch you on the flippity flop.